All right, so let's see. I think the last one cut me off just a little bit. I was talking about, um, electromagnetic radiation. The gamma radiation is the highest frequency radiation that there is. It also is the highest energy. Um, there's an entire electromagnetic spectrum. Um, you have things like X-rays, which are lower frequency than this, and then ultraviolet and visible light that the human eye can see, and then below visible is infrared, and then below infrared is microwave, below microwave is radio. So that's in fact the entire what we call the electromagnetic spectrum. So gamma rays are just the highest end of the electromagnetic spectrum. All right. Let's see. So one of the things that happens is in the upper atmosphere, you got to think about what's our atmosphere made of. Of course, there's oxygen. We know that. We breathe the O2 molecule. The animals need it to live. But most of our atmosphere is actually made of N2, the nitrogen molecule. And so way up in the atmosphere where the cosmic rays are raining down. Of course, they're hitting all parts of the atmosphere, but they get absorbed on the way down. So there's a lot less of them at the ground level. But when these nitrogen molecules that are floating around at the upper parts of our atmosphere will sometimes be transformed used with these cosmic rays into a carbon-14 atom. This radioactive isotope that we encounter in our in everyday lives. Now, the nice thing when it comes to dating, dating things using carbon-14, is that the amount of carbon-14, while a body is alive, whether it's a plant, well, I shouldn't say body, but while an organism is still alive, the amount of carbon-14 compared to the ratio of carbon-14 to carbon-12 is relatively constant, right? That's really important. So that's a really important idea that we're going to use to figure out the date of dead things like dead humans, right, from thousands of years ago. We can figure out how old they are from the amount of carbon-14 that remains in the remains of the human. Or whatever. It doesn't even have to be a human, right? It could be a plant. It could be an animal. Or anyhow, so that's where you get this nice constant rate of carbon-14 being produced, and so living things that use carbon, which is pretty much everything everything that's alive, practically on our planet, they're going to consume some of that. In one form or another. Plants do it as well as animals. Some of the carbon-14, which is nice, and like I said, over their lifetime, while the creature, plant or animal is living, that carbon-14, that amount that it's getting is constant. Keep that in mind. Just kind of put that in the bank and think of it. We'll think about it a little bit later. All right. All right, so let's look at these questions. So the origins of radioactivity go back to I'll tell you why some of these answers are wrong. Like the military activities in the mid 20th century. In fact, that's at the end of World War II, we created two fission bombs. Those are called atom. Those are also known as atom bombs that were dropped on Hiroshima and Nagasaki in Japan. All right, so that those were the fission bombs. Um, the Industrial Revolution 2 centuries ago. So. In other words, part A is wrong. All right, radioactivity has been around, since the beginning of the universe, pretty much. Okay, so let's see. So certainly not 2 centuries ago. That's not right. At the beginning of the human era. So when humans come around on our, when humans exist on our planet, which is, roughly the modern human is at least 200,000 years old. So it's long before that, and so it's the answer D is the correct one. Long before humans ever occurred, came along on Earth. Before life existed on Earth, there was radioactivity. All right. So D is right. All right. When an atom undergoes a high energy radioactive decay, so let's look at this. It becomes an ion of the same element. No. And that doesn't even make sense. I don't know what an ion of the same element. I think what they mean by that is an isotope of the same element. They're just trying to mix up words here. So A is wrong. B, become an isotope of the same element. Well, that is actually possible, but not with the particle part of radioactivity. That can happen with gamma rays. The gamma rays can do that. I mean, to some, yeah. Anyhow, the gamma rays turns into something to a completely different element. That's usually what we find. Okay, so that's in fact what the correct answer to this is. D, it may or may not turn into a completely different element. So that's actually usually what happens when it's a particle. It's called an alpha particle or a beta particle, or a beta particle is just an electron. It can also undergo a transition if it's there are also, remember, electrons are negatively charged. There is a corresponding antiparticle called a positron. So you can actually have positrons, but they will always, if it's a or you can even have just a hydrogen atom, and it'll change the radioactivity will change into another element. All right, so it changes into a completely different element. All right, and we're going to explore that in a little bit more detail as we move on. Okay, so I don't want to cover everything in these first few slides, because I just have so much time. All right. So radioactivity. When radioactivity comes about in the late 19th century. For example, there was a guy named Becquerel. There was also, you've probably heard of her, Madame Curie worked on radioactivity, and her husband Pierre also worked on radioactivity. At any rate, this is one of the things that was discovered. Okay, is when you have a source of, so in this picture you have a source of radioactive material that they're putting a lead block around it. The reason for that is it prevents any radiation from going in. Well, it doesn't prevent it. It just blocks the lead block. The lead will block. It's a great insulator for radiation. But it won't cause any radiation to come out in any in these other directions. It'll only come out where the lead box is open. All right. So what they've done is they put a radium sample. Radium is a natural radioactive substance. They put that in a lead box, and then all the radiation will come out. And so what they've done here is they've passed it through a magnetic field. All right, so there's the little horseshoe magnet. You can see that. By the way, this works whether you don't actually have to have a magnetic field here. You could also have an electric field. So you put some high positive voltage on this side and some high negative voltage on this side. These particles would do the same thing. All right, so in fact, it's called the electromagnetic force because the electromagnetic force acts the same way, whether it's a magnet or an electric field. All right, but that's more into physics than we're going to go. All right, so anyhow, here's what happens. The alpha particle is all right. Let me explain what's going on. So the magnetic field is going this side of the magnet, which is closer to just looking at it, right? This side that's closer to us, that's the North Pole, and this is the South Pole. Okay. And so what happens is, as the particle passes through here, the North Pole, the positive charges, which turns out to be an alpha particle, that they didn't know what this stuff was when back in the 19th century, and so they just used the first three letters of the Greek alphabet. That's where it comes from. Right. I mean, nowadays, of course, we know that an alpha particle, and you guys need to know this as well, an alpha particle is a helium nucleus, right? So and you got to understand that what this is. This is a helium nucleus that comes out of the nucleus of a heavier atom. Radium is an extremely heavy atom. So this heavy helium atom. And it's a helium atom that is stripped of its electrons, right? This is in the nucleus, so there's no electrons involved here with this particular thing. And so this comes out as a plus 2, and it's compared to the beta particle, it is really large, right? So it curves, as it's shown here to the left, if you will. And then the beta particle, which is negatively charged, it turns out that the beta particle is just a little electron. That's all it is. But it's a weird electron in this following sense. It's an electron that, if you think about how you were taught, the atomic structure of matter, electrons exist around the nucleus, and then, then the protons and the neutrons exist inside of the nucleus. So what's going on is, basically, when a beta particle comes flying out of a radioactive sample, the radioactive sample, one of the neutrons has turned into a proton, right? Because basically a neutron is just a proton plus an electron. Right. So that sample has now changed. That one atom has lost, has gained a proton. All right. And so it becomes the next, that just the one atom, not the entire sample, but the one atom is now the next heaviest element on the periodic table. All right. And so this beta particle will curve to the right. You might notice that this thing is curving a little more than the alpha particle. You might wonder, well, why would that be? This one is charged +2. This one's charged only -1. This one is so much lighter. It's close to 2,000 times lighter than the alpha particle. So that's why there's more of a curve. And then, of course, there is a type of radiation that isn't bent at all, and that's called gamma, right? That this symbol right here, this looks better. This symbol right here is the Greek letter gamma. That's the alpha. That's the Greek letter alpha, and that's the Greek letter beta. Right. So 3 types of radiation. You can actually have positive electrons, so they're also known as positrons, All right, so just be